All right. Presenter view is apparently not a thing. Okay, great. So, right, welcome to 67350. It is a pleasure to see all of your, I was going to say smiling faces, but I'm not going to lie, it's like kind of not the vibe I'm getting in the room at the moment, but I'm guessing and I'm hoping that will change as you come to see the joy in numerical analysis that I do. This is a graduate level course in numerical methods and sort of the first time that it's been offered as a TQE for the department, which is why I'm guessing many of you are here, as much as I know that you're all here for the joy of, writing convergence proofs. In any event, my name is Justin. I will be your instructor. We'll hear from our TAs, Mark and Leticia, just momentarily. Today's lecture is going to be the usual thing where we have a bunch of boring administrative stuff at the beginning, and then we'll dive into some of the easier technical content of this course today. In general, I think the sort of arc of 6-7, sorry, they changed the number on me, 67350, it sort of starts out easy, ramps up somewhere in the middle of the semester when we're talking about like iterative methods, conjugate gradients. I think the mathematical content gets a little bit heavier, or at the very least a little more abstract and index heavy. And then toward the end of the semester, we do ODE and PDE, and that actually, I think, in my mind, is a little easier. So before we get started, we're going to go through all the basic stuff, like what is this class, what is the basic timeline of assignments and so on, and then we'll talk about some of the basics of numerical computing. So again, my name is Justin. I'll be your instructor for the semester. This is a class that is very close to my heart. I actually wrote the textbook, actually as a graduate student, so it's been a long time because I'm old. But in any event, I'm hoping that in addition to seeing all of you guys in lecture, you'll come join me in office hours, which will be Tuesdays at 11 to 12 at my office, which is in the Data Center. This class, for some reason, is being offered in the math building, which is far away from me, but that's good because this room actually works pretty well for this, this format of lecture. We have 2 TAs this semester. If you can get all of your friends to register for this course, we can get a 3rd TA, but you didn't hear from me. Specifically, we have Leticia and Mark, both of whom are very experienced in the general area of this course, although because this is the first time this course is offered, of course, they're going to be, we're all going to have to figure it out together a little bit. So Leticia will have her office hours, I guess 1 to 2 outside of D4 to 75A, which is not so far from my office. So if you find my office hours, you'll find hers. And similarly for Mark, but he'll be on Tuesdays and Thursdays, 2 p.m. to 3 p.m. All of this information, incidentally, is on the course syllabus, which you can find on Canvas. So hopefully you've all gone through that material. So incidentally, the syllabus, or sorry, the Canvas website and all that kind of stuff for this course is very minimalistic. This is a very straightforward class format-wise. We've got lectures, we've got homeworks, we've got assignments, we've got quizzes. That's it. So there's not like a super complicated digital footprint for this class. So there are a few online tools that you should be aware of. We'll use Canvas for like posting your grades, and that's sort of the central hub for this course. On the Canvas, I will post chapters of the book. Please do not buy my textbook. Like it's just not worth it. Like there's chapters there. And moreover, actually, what we'll be doing, I'll talk a little bit more about this in a second, is going through a new edition of the textbook that I'm working on. So actually, it'll be slightly out of date if you go buy the book. If you really want a copy, I have them as like a doorstop in my house. So please just tell me. If you have Q&A, we will put those on this Piazza website. I think at this point, students in 2025 are pretty familiar with this. I believe we'll use Gradescope for grading. Are there any other tools that everybody needs to know that I can't think of? I think that's about it. So again, standard class. I think many of you guys are grad students or senior undergrads and very familiar with this kind of format. The textbook for this course is called Numerical Algorithms. It is by Solomon. I happen to think it's one of the nicer treatments of this particular material, but I'm biased. But this textbook is very well aligned to this course. Basically, we will be going linearly through the chapters, but we will be skipping some. In particular, like there's a bunch of chapters on very specialized optimization methods that sadly in the course of a semester here, we won't have time to get to. What I'm going to do is release the book kind of 1 chapter at a time in advance of the lectures that cover that particular material. So you can find all of the chapters on the course Canvas. I'm sorry, I'm like waking up. This is the first time I've taught in a year and a half because I was just on sabbatical, so I've got to remember how to do this. One thing that I do ask of everybody in this room, we're all friends here, so I'll tell you that you don't need to share PDFs with the outside folks. These are PDFs of a draft of a second edition of a book. You don't need to feel like you're sticking it to the man if you like post them somewhere publicly. All it does is just dilute the stuff that's out there. The first edition is online anyway and it's free. So like it really, as a favor to me, please don't share those PDFs because otherwise there's a quality control issue there. If you find typos in the book, you'll be one of many people to do so. Do let me know. We offer vanishing amounts of extra credit in this course for typos and slightly more extra credit if you find a substantial bug in this textbook. So for example, last year somebody noticed that the very first example in the very first chapter was completely incorrect mathematically, that's my bad. You know, please help me improve this thing. If you find a mistake in this book, of course, you will be honored forever by having your name in the acknowledgments somewhere. Okay, so now all the stuff that you guys are all dying to know. So here's how 67350. This is how this class works. So in terms of your grading, the cadence of this class is extremely regular. On the syllabus, I link to a Google Sheet. You guys should all find that link and maybe even just keep it open as a tab on your computer because it gives the topic of every single lecture. If this camera was successful, I will link a YouTube video. 50% of the time it is, 50% of the time it's not. And it has all of the dates of everything except the final exam. Some puzzling thing about MIT that I don't understand is that they don't tell me the date of the exam until midway through the semester. So as soon as I know the date of your final exam, you will too. But essentially the way this course works, there'll be 5 homeworks total. The cadence is once every 2 weeks roughly, but it gets shifted around a little bit due to holidays and due to the midterm at some point. There is a final exam and a midterm. There's also weekly check-in little quizzes that will start next week. So we do not have one this week. Those will be on Fridays. And essentially your responsibility on Friday is going to be to log in, take the world's easiest quiz, and then submit it. Okay? And it's once a week. Here's the thing that I have learned teaching at MIT is that if I don't make a structure like this, you people won't even open the course materials. And so these quizzes are intended to be easy. They are intended not to require like a whole like bunch of scrap paper or anything else. They're just multiple choice. So hopefully it'll be the case. We're kind of writing them on the fly, so chances are 1 or 2 problems will be too hard or have a typo or something. Obviously, if that happens, we'll just give you all credit. My goal is to give you a good grade. Cool. And then always, I kind of put this at the end, there is a little bit of discretion for participation. There's nothing worse than lecturing to an empty room. This course is filmed. If I find that like just nobody is coming because of that, then I might do something annoying, like post the videos a week late or something. So really, I'm hoping to, I was gonna say to learn all of your names, but the reality is, like, let's be real, that's not gonna happen. But I'm hoping to at least see all of your smiling faces in this lecture, to hear feedback from you, to see you in the office hours, all that good stuff. So it's 2025, so I've been told I am supposed to share with everybody in this room an AI policy. Here's my AI policy, don't use it. It's very simple. If you want to use AI tools like ChatGPT, whatever, as a study aid, that's fine. Like you can talk to it like a dummy. As a warning, I have played with these a little bit and put some of our assignments and course material in there, and it often gives incorrect or inaccurate answers. If you use this on the homework, you are cheating in this course. Okay? Here's the deal. Like for some reason, students react very negatively to this, but the way that I see it, like when you were in school, there were calculators, but you still learned arithmetic. The reality is numerical methods is very similar. A lot of these calculations are very common. People have been doing numerical methods since like the 1920s. And so, yeah, a lot of times you're going to be able to put questions into ChatGPT and get a reasonable, if not perfect answer. But from my perspective, that would be the same as using a calculator on an arithmetic exam, okay? So here's the deal. I don't like, oops, there's a typo, students. I do like students. What I don't like is students who cheat. This is a graduate course at MIT. If we detect that you are doing that, you will fail this course, okay? There's no negotiation, none of that. All right. That said, now that I've gotten the grumpy old man part of our lecture out of the way, the reality is that I love this research field. This is an area I have been in forever. I wrote the book. I worked in industry in this area. I built a whole lab around this topic, and I want you guys to love it too. And so essentially, I'm hoping that people in this room will really stick with it. This is a course that I think for many of you is probably like the last math class you'll ever have to take. I know that. This is a TQE. I know how it is. And because of that, it might be quite challenging for folks at certain instances. So please come to office hours, get help, interact with us. This is a group of people who like really is passionate about this area and wants to share it with everybody in this room. But we can only do that with your help, right? If I don't see your faces, then it's very hard for me to respond if something is going wrong. If you're not following something, it's perfectly fine to just reach out and say, hey, I don't know what's going on. I'm gonna come to your office hours. Can you just cover this topic again? Is like a totally reasonable question, okay? Similarly, if you're stuck on the homework, I'll give you a hint, which is if you just hang out in my office and do your homework there, you'll get it done a lot faster because I have no filter. I'll just give you the answers. And I'm not ChatGPT, so that's okay. Similarly, you can make ample use of Piazza. We've got Leticia and Mark have office hours. They're actually kind of strategically laid out because our assignments are due on Wednesdays. So the office hours are Monday, Tuesday, Wednesday, Thursday because there are late days. You can read the policy about that in the syllabus. In general, I can't help but give a little bit of life advice before we embark on our numerical analysis journey together. Here's the deal. This is a graduate level kind of mathy course in the computer science department, which means that I expect you guys to be responsible and active studiers, right? So the homework problems are going to be tricky. Well, some of them are not so bad. And because of that, what that means is that what I have not done is, in fact, sadly for Leticia, she added some problems on the homework that were easier and I removed them because I think it is on you guys to come up with easy homework problems and then answer them. And if you can't, then come to office hours and work through them with me. The textbook has on the order of 20 problems at the end of every chapter that range in difficulty. They're not for credit, but you absolutely can give them a try. It's a great study aid. Moreover, this is a class on algorithms that actually mostly can be done by hand. Right? So we're going to talk about like matrix factorization and root finding and all that stuff. A good way to kind of sanity check your understanding is to actually, like, for example, take a 3x3 matrix and try to invert it using one of these methods. And if you get an answer that doesn't work, then like, obviously there's a gap in your understanding, right? This is not a class where like checking your understanding is like a very subtle thing. Like there's a method for solving problem X. I try it, it didn't work, something went wrong. Okay, and so that's like the kind of thing that like in an undergrad class I would put on the homework and just like kind of force you guys to do by hand. But in a graduate class, I'm not going to do that. So it's up to you to check your understanding. I'll get off my soapbox now, but that's essentially my kind of high level advice. Okay, so every semester this course attracts a slightly different audience, and actually the enrollment is a little larger than we anticipated. So just for my own information, I'm a little bit curious to know everybody's background. Here's the good news, you are all welcome in this course. I'm not gonna check the prerequisites. Be careful if you look at this course material and you think, I don't really know what's going on, then come talk to me to make sure that it's a good fit. That said, just roughly, how many of us are in computer science? Oh, wow. Math? Some kind of flavor of engineering, humanities. Oh. I used to teach in schools. Anyway, okay, undergraduate, master's, PhD. Cool, that's an even split. I don't actually really know what I was intending to ask for your math background, but if you're uncertain, do come talk in office hours. I see a hand here. Yes. You're raising your hand for math. Yes, I'm with you. Yeah, 100%. Yeah, I'm pro math. If you were anti-math, this is not a class for you, and I feel strongly about that. So this is not negotiable. Okay. Every semester when I teach, despite it being in the course description, I get people that come up and ask at the end of lecture, what are the prerequisites? I am actually, I think, the only faculty member in my floor of CSAIL that has no MIT training, meaning that I don't know the course numbers here from like, birth. So here's the thing. If you're wondering, from my perspective, the prerequisites for this course are linear algebra, multivariable calculus, and coding. We're going to use Python in this class. You can map that onto the MIT course numbers as you wish, or if you're not sure, you can send me the syllabus of the class that you took, and I'll take a quick look. Now, when I say, the prerequisite is linear algebra, I mean like comfort with linear algebra, not like I took it 10 years ago and I haven't thought about it since. Like we're going to be doing tricky calculations that rely on pretty good understanding of these topics. If you haven't taken these courses in a while, that's okay. But do put aside some extra time in the first couple weeks of this course to kind of dust off that skill and get used to it. And again, come to my office hours for help. We'll help you. It's fine. So as like sort of a typical example, I thought I would put a very simple proof here of a sort of an equivalence between two different expressions to give you an example of the kind of notation that this course is likely to use, and to give sort of a visual representation of maybe the kind of content that you should be able to be comfortable with coming into this course. If this style of proof is uncomfortable for you, that could be okay, but do come talk to me. So here are the kind of basics thing that we're doing here. Essentially, we're writing an expression for least squares. By the way, in the textbook, we'll use bold letters for vectors and capital letters for matrices. And basically here, we've just taken ax minus b and expanded it. So the kind of identities that we're using here are a few things. So for example, hopefully you know that like if I take, this classroom is not great for short people. Wow. I'm gonna have to bring a stool. This is embarrassing. Okay, so for example, if I want to compute the norm of a vector x, right? Here, you might not have seen this notation before, oops. But the subscript 2 is going to be the 2 norm, like the square root of the sum of the squares. Because in this class, we're going to have more than one norm. And then the 2 up there is square. This notation is a little weird because there are 2 different 2's and they mean kind of 2 different things. But like, so if you look, what kind of identities are we using here? Well, we're using the fact that the 2 norm of a vector is exactly the dot product of the vector and itself. And in this class, we're going to think of vectors as column vectors, so like matrices that are like n by 1, right? And so one way to compute a dot product is going to be to write x transpose x, right? And so if you kind of look at the proof on the screen here, you'll see that basically that's the main identity that we're using here to derive this formula, plus some associativity and so on. Any questions? I'm talking too fast. I had a lot of coffee this morning. Okay. Similarly, we are going to require a little bit of calculus in this class. In particular, the main things that we're going to need are the definition of gradient and Jacobian. These days, because of PyTorch, I suppose that's like a little bit less of an uncommon assumption than it used to be when I taught this 10 years ago. And eventually, we're going to need Lagrange multipliers. Now, this is a concept that I think is probably rusty for many students that took multivariable calculus a long time ago. Lagrange multiplier is the way to like, remember like if I want to compute the minimum of a function, I take the derivative and I set it equal to 0. If I want to take the minimum of a function subject to some other function equaling 0, now I need a Lagrange multiplier. I've posted chapter 1 of the textbook already on Canvas, and it actually goes through my preferred way of deriving Lagrange multiplier formula, so you can take a look there. I find that oftentimes in multivariable calculus class, they derive it by sort of mystical, like magic realism. But the reality is that Lagrange multiplier is a very reasonable object if you just draw a few pictures and kind of understand. So I would encourage you to review that. We're not going to need it for a few weeks, so you got time to catch up on that topic. But it is one that's going to show up a little bit like as soon as we start talking about least squares problems with constraints. There is one thing that I think is a little unique to this class and might be the first time you've seen it. Now, there are optimization problems out there in the universe that solve for numbers, like find me, I don't know, the price of potatoes that, optimizes the trade-off between cost and sales. I don't know, I'm bad at coming up with these things on the spot. There are problems whose unknown is a vector, but there are also a lot of problems in computer science whose unknown is a matrix, right? So in this class, we're going to need all 3 of those things. Now, I think if you've taken multivariable calculus, you've probably thought a lot about problems whose unknown is a vector, right? Like minimize f of x, where x has a bunch of numbers in it. We're going to generalize that ever so slightly to problems whose optimum, or the thing you're trying to compute, is actually a matrix of values. And so one thing that you should take a look at the book about is a little topic that you may or may not have encountered before. This one is okay if you haven't, called matrix calculus, where essentially you have a function, like g here, which inputs a matrix and outputs a scalar. Right? We're used to functions that input vectors and output scalars, so this is a little bit different. And just the same as there's a lot of different identities out there in the universe for like differentiating, functions of one variable or functions of multiple ones, there's also a bunch of identities for differentiating functions of matrices, and they're super useful. Like essentially, You can do all the calculations in this class without matrix calculus, but you're going to lose a lot of time. Okay? So let's do a simple example just for fun. Let's say that I have of f of a is equal to the Frobenius norm of a squared. Anybody remember what the Frobenius norm of a matrix is? It's okay if you haven't. Yes? Yeah, that's exactly right. So our colleague said it's basically like the vector norm, but just over all the entries of a matrix instead of just the column. So in particular, this is the sum over elements ij of aij squared. Cool? So first of all, do we all agree that f here is a function that inputs a matrix and outputs a scalar? See how this kind of thing works? And so we might want to find the minimum of f. This is, I know, a very difficult problem. Anybody have any guess what the minimizer is? This goes easier if you speak up. Yes? 0, that's right, right? I mean, the same way like a vector with minimum norm has 0 elements, yep. Okay, so how could we prove this using unnecessary machinery from calculus? One thing I could do would be to differentiate f with respect to a, and then set it equal to 0 and show that it's minimized at 0. So in particular, one thing I could do would be to differentiate with respect to every element of a one at a time, right? In which case I'll compute the partial derivative, dAij, like that. Now this is d over dAij of aij squared. If you're wondering, the calculations in this class will get way harder than we do today. Anybody want to help me out? What's the derivative of this giant sum with respect to one of the elements of A? Yes?
2 times AI.
That's right, 2 times aij. By the way, hopefully you can all read my handwriting. If you ever can't, please stop me. I'm also going to try and be in the habit of reading things out loud as I write them, but occasionally I forget to do that. The feedback I got in the very first course I taught at MIT contained the phrase serial killer handwriting, which is not something that I ever understood and made me feel a little confused. But in any event, I think the takeaway is that apparently I can't write very cleanly. Okay. So this is one way to do this kind of calculation, right? Take the derivative of f with respect to every single aij one at a time, and then set it equal to 0. What matrix calculus is going to do is to take the gradient of f with respect to a, which is kind of like just a giant object that takes the derivative with respect to every element of a at the same time, right? The same way that like gradient of f of a function, of a vector rather, gives you like df dx1, df dx2, df dx3, right? So first of all, what is this object? I think a good skill to have in this class is to like always look at expressions and ask like, do these compile? You know, like, do the indices work out? Do these matrix products make sense? All that good stuff. So this is going to be a matrix. Do you see that? Because like here, right, there's a df aij for every single I and every single j. And essentially what we showed in this little, like, derivation is a little strong, is that the gradient of f with respect to a is going to be 2a. Does that make sense? So we're going to do a lot of calculations like this in this class. So for example, if you look at this function g on the screen here, here g inputs a matrix A and outputs the sort of like outer product of some vector w with respect to A. So here the unknown is A, it's not w, so w is like a constant. And so there's some identity that says like if that's your function, then the gradient of that with respect to A is ww transpose. And there's a whole table of those. The same way that you probably learned in undergrad calculus, like how to differentiate cosine and how to differentiate x squared. There's a bunch of these identities there. So in any event, this is sort of an efficient proof technique that's extremely useful in numerical methods, so it's good to get used to it now. If you come back a year from now and you take my geometry class, we do kind of the opposite of that. So we're going to get used to Einstein-style notation, where you have like indices that go up and down and like summation every which way, which is more convenient in differential geometry. But the good news in this course is we will not encounter a curvature tensor, so we don't need that kind of thing. Any questions so far? I'm talking fast. I'm sorry. It's a bad habit. You know, in my teaching training, they said you're supposed to ask a question to the room and then count to 10 and make it really awkward for the students. Okay, I feel like I've succeeded. Excellent. So let's talk a little bit about the content of this course, and then we'll dive into the actual technical stuff. So 6 67350 essentially is an applied numerical methods course. Our goal is to survey the broad horizon of different methods out there for numerical analysis. And in particular, as we go through these methods, I want to highlight applications that we see in computer science. This course is going to be a little bit less proof-based. We're not going to like prove convergence and the, like under some weird Lipschitz assumption of this algorithm under that circumstance with that initializer, that kind of thing. We'll leave that to my colleagues in the maths department. And more, my goal in this class is to give everybody in this room a lot of intuition, where you see some messy problem in computer science, and we have this big toolbox of numerical algorithms out there, many of which, by the way, are coded for you. The nice thing about this class is like a lot of the coding is actually very messy, but like you don't have to do it. Fun fact, a lot of it's in Fortran. Which years ago, as an April Fool's trick, I told the students they'd have to do their assignments in Fortran, and I got some emails that I will keep forever. In any event, essentially, I think when you take a class like this, the way to think about this toolbox is that there's sort of two different hats that I want you to put on, and hopefully our assignments are going to reflect this a bit. On the one hand, the good news is that numerical algorithms, especially in the first half of this course, like when we talk about numerical linear algebra, we're going to cover a lot of algorithms that you will never code in your life unless there's like a very special reason why you need to do it. So for example, we'll talk about different matrix factorizations, LU, QR, SVD, some fourth one that I'm not thinking of. And all of those methods, there exist extremely efficient code bases out there that probably use algorithms that are more advanced than what we'll cover in lecture. And so the main thing to be aware of when you're using those kinds of methods is that all of these different tools exist, and you need to understand like, oh, I've got this messy problem in numerical methods. This is the matrix factorization I'm going to need, right? And so we'll actually go through some research papers drawn from machine learning, from computer graphics, and other disciplines that essentially boil down to like, oh, I started with this messy problem in the applied universe, but actually I can kind of distill it down to requiring one of these matrix factorizations, maybe with like a cute code around it, and then put it back to read off the solution to my problem. Because of that, I would consider the coding assignments in this class to be on the easy side. Now, when I say that, what I mean is that coding in this field is wildly frustrating. Because if you get, and Leticia can speak to this because she's my student and she does even yuckier numerical methods. Essentially, all of us make sign mistakes. I'm going to make many in this course. And if a single character is wrong in your code, these algorithms tend to fail, right? So it's like one of these weird areas where you're like, implementation is 10 lines of code, but man, you got to check the 10 line real carefully. Now, as we get later on in this course, we're also going to take on a second role, which is a designer of numerical algorithms. Like eventually, we're going to leave the space of problems for which there exist nice kind of prefabricated code bases you can use. And then we're going to have to talk about like how to cook up bespoke algorithms for solving numerical problems that you see in different domains. Right? So in particular in optimization, sometimes like we'll take a look at the objective function of our problem. We'll notice, oh my gosh, it has this nice structure that I can leverage to solve it really quickly. But now the coding becomes a little more tricky, and we have to convince ourselves our algorithms work. Right? And so that's sort of what I'm hoping the message is that you get out of this course. It's not like, for example, I used to teach 6006 or whatever the number is these days for the undergrad algorithms class, where like, you learn dynamic programming, but like the reality is there's not some like code base out there that just does dynamic programming. It's like a technique for solving a bunch of algorithms problems. The reality here is there really is a code base for solving a lot of these problems, and you should use it. And in fact, oftentimes if you find yourself coding one of these basic numerical methods, something has probably gone wrong. Right, so essentially that's going to be the key skill in this course, is to start with some messy computational problem, reduce it to a numerical problem, like something of this sort of boring abstract looking form, right? Choose the appropriate numerical method for solving it, and maybe make some adjustments to that method depending on this situation, and then to actually just implement it. And one thing that we're going to find in numerical algorithms is that success is a very squishy notion, right? This is different than, for example, in like undergrad algorithms class. Like, I don't know, I sort a list of numbers, I run my piece of code, either they come out in order or something went wrong, right? In numerical methods, one thing we're going to learn starting in like 15 minutes is that all of these algorithms have tolerances, right? Like we solve them within 10 to the minus 5 or something like that. It's pretty rare to solve a numerical algorithm exactly, numerical problem. In fact, if you look, if you're an algorithms person and you want like a good example of a very simple problem that's, to my knowledge, hard to solve in closed form, think about eigenvalues of a matrix, right? Like even if I have infinite precision arithmetic, it's not obvious how to actually just write an expression for eigenvalue, yeah? So because of that, we're gonna also spend a lot of time not just designing these algorithms, but then also building some intuition for like, how well should it work and how efficient is it? And often those two things get traded off. Like the longer I run my algorithm, the closer I get to a solution or something like that. Does that make sense? Okay. So let me give you a quick sort of overview of the topics we'll cover this semester, and then we'll dive right into the technical content. I'm realizing I left my notes in my bag, but I'm an overconfident tenured professor, and I'm going to try and do it without. Okay. So this course is going to, it basically follows the arc of almost any numerical methods course. It's not terribly creative in that sense, which means that we kind of start with linear algebra, and then we start introducing nonlinearity in different fashion. So this course is going to begin in the first, I'd say, 2 or 3 lectures, talking about the really low-level boring stuff, right? Like how do you represent a floating number on a computer? What does it mean to have error? What are the trade-offs? Interestingly, like I think all of us think of this as a really boring topic, like something that the IEEE people solved like 150 years ago. But the reality is that actually we're reconsidering it in like the 2020s. For example, Google recently released these tensor cores with their own special floating point format. And there's really good reason for that, which is that essentially the trade-off between precision and range is very different in machine learning than it is in like scientific computing, right? So a lot of these sort of classical topics are actually getting reconsidered in the era of like big messy data sets and GPUs and all that good stuff. After that, we're going to spend a lot of time on numerical linear algebra. Now, numerical linear algebra, typically you learn this pantheon of different ways to factor a matrix, right? So you might, we'll start with the Gaussian elimination algorithm. Many of you, hopefully all of you, have encountered some version of this in the past. So like when you took undergrad linear algebra, at least when I did, 25 years ago, a thing that for some, like a fun party trick that I feel like your undergrad professors have you do is like row reduce a matrix 1,000 times by hand. But we're going to see that that is like a useless party trick because actually there's this, essentially you're just doing a very boring algorithm manually every time you do that. It's something you can just code. That's called Gaussian elimination. And then we're going to show, moreover, if we kind of keep track of the steps of Gaussian elimination, this suggests that we can factor matrices as a product of a lower and upper triangular matrix. This is called LU factorization. Then we're going to talk about sort of, I think the way to think about it is for every topic you see in like linear algebra, we're going to take that topic and then adapt it to an algorithm, right? So the same way as like solving linear systems, we'll do with an algorithm. Then we'll talk about specially structured matrices, like positive definite ones, and how you can solve them faster. Another thing that you talk about in algebra class is column spaces and row spaces. And we're to see that a particular factorization called QR kind of encodes a lot of the big ideas that you might have seen in that regime, involving like what is a good basis for the column space of this matrix, something like that. We'll see that that's useful for least squares problems, among many other things. And then finally, we will end with eigenvalue problems. We're going to have a short digression in this course because I feel like a thing that happens with eigenvalues as you come out of your undergrad linear algebra class, like if I ask each of you guys, like, what is an eigenvalue? You say, oh, yeah, it's this value where you have this vector x and this number lambda and ax equals lambda x. And then my follow-up question would be, okay, where, like, name for me one computational situation where I would actually use that expression. And then I would say about 85% of the students that I encounter in computer science are unable to do so. So we will spend some time in this class actually talking about why eigenvalue problems are extremely natural and interesting. It's not just like a fun party trick that mathematicians do to torture undergrads. And then we will go back and talk about algorithms for solving eigenvalue problems. In fact, we'll cover one of my favorite algorithms in the entire world because it's just like so beautiful and interesting and shocking, which is called QR iteration. For those of you who are familiar, you can take any matrix and factor it as a product Q times R, where Q is orthogonal and R is triangular. If you don't know what that means, that's okay. And then QR iteration is like 2 lines of code. You factor it as QR, and then you replace the matrix with RQ. And you just iterate that, and we're going to prove that this converges often to a diagonal matrix of eigenvalues, which is like mind-blowing to me. And that'll fit together all of our linear algebra stuff. After that, sadly, we will leave linear problems behind and move on to nonlinear stuff. We'll talk about root finding and optimization, so finding zeros of functions, and that's, of course, related to minimizing functions, right? Because what is the typical way that we minimize a function? Well, we set its derivative equal to 0, right? So these things are clearly linked. Of course, you say, but Justin, what if it's not differentiable? In which case, we'll talk about a few strategies for solving those problems. We'll also talk about constrained optimization algorithms. That's where those Lagrange multipliers are going to come into place. We're also going to briefly introduce a notion called the KKT conditions, which are sort of an extension of Lagrange multipliers to inequality constrained problems, and show that actually the algorithms, once you understand actually just the calculus of it, the algorithms themselves are not terribly complicated. And then finally, we're going to kind of close our loop with linear algebra and say, let's say in particular, I know a lot about my objective function for a problem. In fact, I know that there's like certain problems that are just really important. Then maybe I should actually go back and revisit some of our linear algebra problems in the context of optimization. So to give you an example, let's say that I want to solve a problem, a linear problem like ax equals b. And moreover, let's say that a is positive definite. Then here's a kind of interesting thing I can do. I can define a function, which is 1/2 x transpose ax minus x transpose b. If you're really good, you can calculate the derivative of this in your head, but I don't expect that. For now, I'll just give it to you, but you should check this at home. That the gradient of f with respect to x now is going to be ax minus b, right? So in particular, if I try to optimize this f, that's actually the same as trying to find a solution to ax equals b. Do you see that? So this is going to give us a totally new perspective on numerical linear algebra. Like the first part of the course, we're going to use methods like Gaussian elimination that directly solve linear systems. Then, to kind of wrap up our discussion of optimization, we're going to go back and say, oh, wait a second. Like if I apply my optimization algorithm specifically to this function, I can now derive a whole new set of algorithms for solving linear systems, right? And so this is going to lead to algorithms like conjugate gradient method, which are extremely efficient and also have a lot of nice properties when your matrix is like ginormous. So for example, if you're in back in the day, for a little while, I worked at Pixar working on cloth simulation. The matrices there are really, really large, positive, definite, and sparse, as they are in many corners of physics. And these are the kinds of algorithms that use in that domain because inverting these things just takes too long. So like an approximation is okay. Okay, finally, the last two topics of this course, which in my mind are actually a little easier than number 3. We'll talk about interpolation and quadrature. So this is like if I have a function sampled at a few points, how do I kind of guess what that function looks like in between? Obviously, this is sort of an ill-posed problem in some sense, but there's some nice things that we can do. Quadrature is all about computing integrals of functions given some samples. This is going to look a lot like high school calculus, like the trapezoid rule, but we're going to derive some nice error bounds. And then finally, we will conclude with some differential equations. So we certainly will talk about ordinary differential equations, so like f equals ma. We probably will not get to partial differential equation like finite element method, but we'll see. I'm talking very fast today, so maybe we'll get there. My goal is to conclude this class actually with a fun machine learning application. So if you might have encountered something called normalizing flows or neural ODEs, it's actually a beautiful application of the kind of ODE theory that we'll talk about, coupled with the Lagrange multiplier math that we did a couple weeks before that, because you need to kind of back propagate through the solution of an ODE. This is something that, believe it or not, existed before neural networks. It's called the adjoint method. So we'll actually derive that, and that'll hopefully be our last lecture in this class. It's kind of a fun capstone way to see a modern application. Okay. I feel like I'm talking a lot. So we sort of concluded our basic course overview, the basics of this class, grading, all that good stuff. I should pause for a second. Are there questions about topics, background classes, prerequisites, office hours, any of that good stuff? Okay. All right. In that case, sadly for you guys, we'll get started with some technical stuff. Yes. Thank you.
Are you measuring class participation?
How am I measuring class participation? With vibes. Yeah, 100%. What that means is that most likely your score will only go up unless there's something that really went wrong. Yeah. Any other questions? Yeah, 100% discretionary. By the way, in case students haven't noticed this already, at almost any class you take in the university, if your grade is borderline and you were nice to the professor, like, there's good odds that like maybe it gets rounded up. But not that that would happen in this course. Okay. So we're going to start this class by talking about the lowest level consideration, which is the basic idea of how do you store a number on a computer, what does it mean to do arithmetic, and how do we deal with the fact that there's like a lot of numbers out there in the universe, right? Yeah, she gets it. So like essentially we need to talk about what are the standards for storing values on a computer, and the fact that there's engineering decisions to be made here. I think a lot of us just like open up Python, they make something of double type and you don't think about it ever again. But there's actually a lot of trade-offs between different number representations that are subtle and very important to consider, okay? So to kind of lead off, here's a very simple prototypical example. This is a piece of code in C++, probably 1.0 because I'm old. I feel like these days there's like fancy templates and things. Let's say that I make a double value x and I make a new double value y, which is x divided by 3. It's a very complicated piece of code. And now I check, is x equal to y times 3? I mean, so like sanity check, like roughly what should y equal? I'm intrigued by the finger motion here. That's yes, the universal motion for 1/3, yes? Okay, so right, so y is probably equal to 1/3. So initially, it feels like, oh, well, 1/3 times 3 is 1. That's x, yeah? So what should this code print out? Yes? They're not equal. That's right. What goes wrong? Yes?
Like you can't represent 1/3 in binary because it's like infinitely long ceiling.
That's exactly right. Yeah, so our colleague is right. Any calculation that we do with a floating point in it gets rounded up or down, right? So what is 1/3? It's 0.3333333, approximately. But on a computer, like, can I store an infinite number of 3s? Of course, we do this in binary in reality. No, so what happens is it gets truncated. I cut it off. So when I compute 1/3, I don't actually get the number 1/3, at least in double precision. We'll come back to that in a bit. What I get instead is some number that's kind of like 1/3. Yeah? And so when I run this piece of code, sadly, if I compute 1/3 and then I multiply them back, I might not get the number 1 anymore. In fact, it'll print out that they're not the same. Yeah? And that's because of rounding error. So here's the basic idea and the basic philosophy that's going to happen in this course, which is that expressions that feel mathematically correct, like 1 divided by 3 times 3 equals 1, are no longer numerically sound necessarily. Right? So in particular, in your coding assignments, if I see that double equal sign operator, probably something has gone wrong, right? Because like it's very rare in numerical methods to get an exact equality of anything to anything else. Yeah. And so from this basic example, hopefully you can see that when we talk about calculations in this class, it's not like integers and sort of basic undergrad algorithms in computer science. We have to talk about approximation quality, and that's a really important consideration in this domain, in addition to time complexity and all the stuff that you're used to. So, for example, if we return to this little code segment, does anybody have a suggestion? Like, how could I make this thing print out the solution that I think it should? Yes? That's exactly right. So Alice has a great idea, which is I can take these two values, subtract them from each other. Now, in reality, I'd like that number to be 0, but it's probably not quite. But if I take the absolute value, it's probably awfully close to 0. So maybe I take the absolute value of the difference, and I say, oh, if that's small enough, then I consider my calculation to be a success. So let's see what that looks like in code. Okay, so again, I know my C++ is outdated now that I'm looking at it. But essentially, notice I've taken my two terms, I've subtracted them from one another, and now I'm checking if they're less than some magic number, epsilon. So epsilon in this expression is something we would call tolerance, right? Now, there's a natural question, which is, what epsilon do I choose? Do we have any suggestion? Like 10 to the minus 8 feels right, yeah? No, I mean, the reality is that choosing that value epsilon is a really complicated matter, right? For some calculations, especially when we talk about things like eigenvalue problems, where we're going to iterate to get the solution, it might be that it's not even just like issues with your number system that's getting things to be approximate. It's that my algorithm itself doesn't know how to solve the problem exactly. And so this is going to require a little bit of knowledge of your number system. Now, in this case, this is a pretty low-level piece of code. So what I've chosen to use is a pretty standard thing, which is something called numerical epsilon. Does anybody have any idea what this is? We'll go back to the definition in a minute. This is the smallest number epsilon for which 1 plus epsilon is not equal to 1. Does that make sense? So it's like the smallest increment I can get away from 1 that is distinguished from 1. I think roughly you can think of it as a small number. By the way, if you go on the Wikipedia page for numerical epsilon, there's like some really cool math out there that shows it's actually a very natural thing to do in discrete number systems. There was a version of this class where I went through a bunch of those proofs, and then I realized like nobody cares. We should do the high level stuff. Okay. Okay, hopefully you understand the motivation. Basically, every calculation we do on the computer is going to be approximate, and that's a problem. So of course, when we look at a piece of code like this, what we really should be doing is thinking about what's going on behind the scenes. Okay? And it's good to be sort of aware of this. If you're ever coding it on your own, something has gone horribly wrong, or you work at Intel, apparently for the US government. And behind the scenes, a lot of these things, in fact, are implemented on your chip, right? Like these are really low-level operations. So let's start easy. Probably we all know that on a computer, we store numbers in binary format, right? This means a big sequence of ones and zeros. We have a binary number system. So for example, I take the number 463. I can write it as a sum of different powers of 2. And then I translate that into an integer format like this, right? So here's a little table. Now, in general, this already kind of suggests the easiest way that I might store a fractional value on the computer. I almost said floating point, but that would actually be wrong. Which would be to basically take this number system and just keep going to the right, right? So I have like 2 to the 8th, 2 to the 7, 2 to the 6, 5, 4, 3, 2, 1, 0. Then I could have 2 to the -1, 2 to the -2, right? So like 2 to the -1 is a half, 2 to the -2 is a quarter, right? And this leads us to something like this. So for instance, the number 463.25, now I add 2 to the -2, and essentially I just keep going with my table. Does this format make sense? So this is the simplest way to store a floating point number. No, I did it again. A fractional value on the computer. And the good news is that, notice that, like for instance, if I wanted to add 2 of these numbers together, I could multiply them by 2 to the 2. Right? Now they're integers again, right? Because I've canceled out the 2 to the -2. Then I could add them together as integers and then multiply the result by 2 to the -2, right? So in fact, if your chip already knows how to do integer math, it also knows how to do math in fixed point arithmetic just by reusing the same integer operations and just kind of reinterpreting them. Does that make sense? I'm rushing a little bit because I want to get to the interesting stuff. Okay. So here's the basic problem. Let's go through it in a little more detail now. Recall that like in our piece of code, we have the number 1/3. Fun fact, the number 1/3 in binary is 0.01010101. At least it was when I calculated it a few years ago. I haven't checked since then. And of course, in this fixed point number system, I probably determine a priori like all of my numbers have 32 bits. In other words, like there are 32 ones or zeros I'm willing to store. Is 32 bits enough to store 1/3? Obviously not, because I need infinity bits. So what do? Well, in the fixed point arithmetic system, I just cut the sequence off at some point. Maybe round the last digit up or down. That makes sense? Now, this is a totally reasonable thing to do on a computer. And in fact, the good news is that fixed point arithmetic is really fast. Yeah? So in fact, until fairly recently, like your graphics card, your GPU, sorry, your machine learning card, like this was the number system that was preferred because essentially integer math on the GPU is blazingly fast, right? And so like when you switch from integer to double, you actually incur a big efficiency loss because the operations get a lot more complicated. Yeah? And so I think there's a reasonable question, which is like, why don't we do fixed point arithmetic for everything on the computer? Like, why is there all this other stuff that seems so much more complicated? Okay? And I think the reality here is, sadly for us, the typical calculations that we do on a computer are not just adding and subtracting, they're also multiplying and dividing. Yeah, I think this isn't too controversial thing to say. And multiplication and division is where fixed point arithmetic really gets into trouble. Okay? So let's, oops, sorry, I forgot. I don't have my presenter view today, so I'm gonna end up like going back and forth with it. Here, by the way, is sort of the formal way to specify a fixed point arithmetic system before we go on to alternatives. Notice basically I need to know a total number of digits, like some number of digits past the decimal point and some number of digits before the decimal point. And those are basically the parameters that I need. Yeah? And like I mentioned in words, you could reuse integer arithmetic. So for example, if I want to compute a plus b, and these have like k digits past the decimal point, then I can multiply them by 2 to the k. Now these are integers. Do the addition using like my old ALU on my CPU, and then put it back. Does that make sense? By the way, like this is what we do as humans. On the computer, it probably wouldn't even, you just reinterpret, the same value. Okay. So here's a problem. Let's say that I do multiplication, and in this case, maybe I only have 1 digit of precision past the decimal point. This is a pretty bad number system. Incidentally, by the way, there's some really weird neural network papers recently that propose like 3 digits of precision for training a neural network, which is wild to me. I don't see how that should work. But that aside, what is the product of 0.1 and 0.1 in binary? Well, one thing you can check is that actually this one still works out. It's 0.01. If you want to sanity check that in like human numbers, right? So 0.1 is 1/2. What's 1/2 squared? Oh my gosh, guys, on 3. 1, 2, 3. Yes, 1/4 or 0.25, which in binary is 0.01. Now here's a problem. In our fixed point number system, what is 0.01? Well, it's just 0. Or maybe 0.1, I don't know, whatever. Yeah? So the takeaway from this example is that multiplication and division tend to change order of magnitude. So for example, notice here, I had 2 values that had 1 digit of precision right next to the decimal point. When I multiply them together, I have the same amount of precision, but it kind of moved to the right? And this fixed point number system really can't account for that kind of thing. Now, this is a common issue, not just on a computer, but also for humans, right? I mean, like we don't write numbers as scientists always in this sort of absolute format, right? So for example, in science, we have numbers that range from like 9.11 times 10 to the minus 31 to 6 times 10 to the 23rd. When I was closer to undergrad, I remember what those numbers are. Yeah, and essentially, it would be really weird if like every time I did chemistry, and I wanted to talk about a mole. This is a mole, right? 10 to the 23rd. That I wrote like 6022000000 a bunch of times, right? That would be kind of clunky, right? And so instead, what we do is we invent something called scientific notation, which is what you're seeing on the board here, right? So the standard is you sort of take the very first digit of your number and you write it before the decimal point. You put everything else past that, and then you keep a power at 10. Yeah. And then essentially, when we add or subtract, multiply, and divide, we carry out those operations, and then we kind of convert it back into this format. And what we're going to see is that that allows us to traverse scales much more easily. Does that make sense? So in particular, essentially, the observations here are that compactness really matters, right? Like, this would be a really weird way to store this number, and moreover, I think, sort of implies an amount of precision that we don't have, right? And some operations are also really unlikely. So is it the case that I'm likely to add 10 to the minus 31 to 10 to the 23rd? Well, in typical scientific applications, that would be pretty rare, right? And so all of these observations together suggest that this fixed point arithmetic system is like probably not it, for a lot of numerical computing. That make sense? Okay. So instead, what we're going to do is introduce much clunkier notation. But essentially, we're going to use scientific notation to store values on the computer. And this is the standard for most numerical methods. Right? This includes things like the double precision floating point and some other things we'll mention shortly. Unfortunately for us, this requires the sort of arithmetic on your CPU or your GPU to be much more complicated. Because now you got to deal with all these different parts of your number as you're adding, subtracting, multiplying, dividing. And they sort of operate in different ways, right? So here's the basic way that you might store a number in scientific notation. You have a sign, like plus or minus, which is just going to sit in front of it. How many bits does the sign take? 1, thank you. I'm going to have the significand. Typically, I store sort of 1 digit before the decimal point and then some fixed number past the decimal point. Okay. By the way, sometimes you call this the mantissa, which I think is a cute name. And then finally, just like you had 10 to the 23rd, you're going to have an exponent here, which is going to be the base. So on a computer, that base is going to be 2, probably. And then n is going to be an integer, which is like the number 23 in the 6 times 10 to the 23rd. That makes sense? And this is called a floating point value. Why is it floating point? Well, essentially, decimal point kind of floats around, right? Like as I multiply by powers of 2, it's sort of shifting around in the number system. Okay? And so when we talk about floating point number representations, essentially they're specified by 3 values, which is a base b. It's very rare to encounter anything other than b equals 2 in computer science. We have a precision p, which is sort of the number of digits that I'm going to store past the decimal point. And then finally, a range of exponents. And actually, it's typical to store a lower and an upper bound for that range. Like sometimes you kind of know a little bit about your computations and you know like, oh, I'm going to deal with big numbers, so maybe it doesn't make sense to like store really small stuff. Right? So notice that in reality, this is sort of, I have to interpret the bits of a number in scientific notation in different fashion, right? I have some bits like the significand that I have to understand as sort of a number in some decimal fashion, and then I've got the exponent n, which is really just an integer, right? So when I add, subtract, multiply, divide these numbers, now I have to kind of deal with all these different pieces separately, and this really is more inefficient on your CPU. Like if you take your calculation, I encourage you to try this at home. Pull out your laptop and like add together 10,000 numbers and do it in float and then do it in double, and you'll see that the double one actually does take a tiny bit more time on your computer. Now, floating point numbers feel really natural, but they actually are like a little weird the more that you think about them. So in particular, like let's say that this is a very typical diagram to draw, like what you see on the screen here, where I take all of the numbers that I can represent in my floating point system, right? There's a finite number of them, right? And I can just plot them on the number line, right? Now, what does that plot look like for a fixed point representation? What was that? Uniform, that's right. It's just like a bunch of evenly spaced points on the line. But now we've done a weird thing, right? Because essentially in every order of magnitude, right, I have like some uniformly spaced set of things where like the exponent is fixed. And then I click the exponent up and suddenly the spacing gets like 2 times bigger than it was before, right? And so I have this really funny number system where I've got like a bunch of stuff bunched up near 0. And as I get farther out, they become more and more spaced. Right? And so for some problems that makes a lot of sense. For other problems it actually doesn't. So like for some calculations you kind of know like my numbers are going to be in this range, then maybe this number system actually is just a way to lose precision. So a few definitions that are useful here. As we already mentioned, machine precision or numerical epsilon is the smallest number that you can represent beyond the value 1. So like in this picture, you can see like what would be machine precision for this little number system I've drawn. Yes. 0.125. Not quite. It would be 0.25, right? Because if we look, there's the number 1, and then the very next thing beyond it is 1.25. Yeah, goes the other way. That's right, to the right. You could ask, like, does it really matter? And the answer is no. It would be a factor of 2. Yeah. The other thing that you need in a system like this is a rounding rule, right? Because at the end of the day, as we already saw, like if I compute 1/3, I get some infinite sequence of digits. I'm going to have to round, and so I need a procedure for actually choosing that very last digit. Now, this feels goofy to go through this much detail, but you actually have to be extremely careful. So for example, let's say I were a lazy chip maker, not to name any names. And I decided like, oh, I can make my CPU ever so slightly more efficient by just always rounding up in the last digit. And now, for some reason, an undergrad, none of you guys, decides to implement their financial software in double precision, which you should never, ever, ever do, right? Because like dollars matter. You can't be rounding them up and down in like weird, willy-nilly ways. But let's say that I did that by accident. And I started adding up all the money in a bunch of different bank accounts. What's going to happen? Well, systematically, the value that I will get will be larger than what it really is. Right? And so all of these little tiny details about designing your number system, like how do you round, really matter. And they have big effects on people's code because people use these things without thinking about it, right? And so for example, if you read the IEEE 754 standard for storing double precision floating point on your computer, it has like 10 different rounding options that you can actually implement in this thing. Like you look and like, for example, evens round up and odds round down or something like that, all of which have different bias. And you have to be so careful. Right? So for example, a very typical rounding rule is rounds to nearest, right? So like thinking like base 10. So if I have 0.7, then it would round up to 1, and 0.2 would round down. But then there's always the question of what do you do with 0.5? Now, for some reason in school, we all learned that 0.5 rounds up. I actually don't know where that rule comes from. It could just as equally round down, right? It's right in between. And so a very typical thing to do is to look at the next digit over, and if it's even, round up, and if it's odd, round down, or the other way around. Now, here's the thing. These are all standards that we can implement. Another very common one is to just assume that the very first digit of your number is 1, right, in binary. This is nice because it saves 1 bit. The only problem is you can't represent the number 0. These are great rules, and initially in the like sort of early days of computers, you know, people all invented their own number systems, coded them up, and then you ran into a big problem, which is I write a piece of code, and now I send it to my friend, and that does exactly the same calculation and gives me a different result. I think something that we all take for granted these days is, like, for example, when I look in this room, I see an Apple computer, I see a PC, I see an iPhone, I see, like, God knows, like, something probably hanging off of your ear. All of these are different processors, and yet we can rely on the fact that if I take the same piece of code and I run it on each of them, then it does all of these little minutiae, like rounding up and down, in exactly the same fashion, right? And this is a triumph of standard-making organizations. Yeah, and so this is a thing that like is really subtle. Like when people came out with the standard for double precision floating point on your computer, they had this big global meeting where they brought people in to like negotiate over what direction numbers round and how many bits to have, you know, past the 0 and whatever. And there's a lot of trade-offs, right? Like for example, maybe in certain corners of scientific computing, I need tons of digits of precision, whereas in like statistics, it's all noise past a few digits anyway. So like if we want one standard for storing double precision floating point on a computer, like what do I do with these 64 bits? It actually requires a lot of negotiation to figure that out. By the way, there's even more subtle concerns there, right? Like it could be that multiplying and dividing takes more electricity than adding and subtracting, right? So like if you have more digits of precision, you actually are affecting the environment, which is crazy to think about. But these calculations are done billions of times per like a millisecond, you know? So this gets multiplied by some huge amount. So to give you an example, here's a very standard thing. It's a 64-bit double. This came out the IEEE 754 standard. I don't remember when this was. I think it was in the 1980s, which was not that long ago. And essentially, when you come up with these standards, the first page are all the stuff that I showed you in the previous slides. So for example, the base is 2. There's precision of 52 digits past the decimal point. The range of exponents is actually quite large. It's, you know, like 10 to the 24, or 1024 rather. But then there come all these special cases that you have to deal with. So for example, what happens when you divide by 0, right? And so there's a special representation for not a number. There's also special representations for plus and minus infinity, which you probably all experienced as you've written code. But what you might not think about is now with every single one of these special cases you introduce, you also have to introduce a bunch of rules. Like what is infinity plus 0? Well, in math, the answer is like, I don't know, you did something wrong. But in IEEE 754, you don't get that luxury, right? You have to actually define an output. I believe the output of that calculation is not a number, but I could be wrong. You also need conventions for rounding, right? Like when do you round up? When do you round down? And then these chip manufacturers slavishly keep attached to this particular standard so that everybody can agree that this piece of code is going to work on every single chip, whether it's an AMD, Intel, or whatever else. Does that make sense? Incidentally, all of these number systems, when they're deterministic, can often introduce different kinds of bias in your calculation. So for example, let's say that I'm adding up a list of numbers, and I even, like I'm clever, I use this fancy IEEE 754 standard, and I know that, you know, evens round up and odds round down. But then for whatever reason, in my particular application, I only ever deal with even numbers. And then actually my calculation is still messed up, right? So it's actually very hard to design a number system that works perfectly for every application, yeah? In that particular setting, what you might need to do is actually something stochastic, right? Like randomly round up and down the last digit if you really care about bias. Of course, that opens another can of worms, which is how do you generate random numbers? And of course, if you do that in the IEEE 7054 area standard, then it's turtled all the way down. But just to give you an example that like this is not an abstract concern and something that people thought about in the 80s and then just kind of like put aside. Just a couple years ago, Google Brain actually decided that this was not the right number format, that the standard that the IEEE put out years ago for people that were doing scientific computing really doesn't make sense in machine learning. Why is that? Well, in machine learning, as you guys, I mean, these days I feel like probably most students in this room have played with some machine learning tool or another. It's fine if you haven't, because that's not the topic of this course. Essentially, what happens in machine learning is we deal with very noisy data, which probably isn't terribly reliable past a couple decimal points. Oh, I already scared one. So in that case, does it make sense to have like 64 bits of precision? Right? I mean, think about like your typical neural network. You've got these neurons, which are like super noisy. You're training them anyway using stochastic gradient descent. So they're like wiggling around like this, right? And for some reason, the IEEE standard says that I am going to maintain every arithmetic operation I do with this thing up to 64 bits of accuracy, when the reality is that my data is reliable up to like 2, yeah? So that's like a really bad savings, yeah? On the other hand, maybe I have a lot of range, right? So one thing you might know is that like some data sets have really big numbers, some have really small numbers. Sometimes as you move through the layers of a machine learning model, they transition from one order of magnitude to another. So essentially what the brain floating point format does is it says we should put more of our digits into the exponent and fewer of them into the actual number, because that's what makes sense in my particular application. Now, this is super cool to me. I mean, these are like problems that people haven't thought about in like 30 years that are getting revisited in this new kind of mode of computation that's very popular today. The only problem is that you and I probably don't have access yet, until you're all CEOs of fancy companies, to like the chip manufacturer you need to implement this kind of standard. So the reality is that we all are kind of stuck using a few kind of basic floating point numbers that are built into most of the cards we have today. Does that make sense? But I think this is a cool example where like just a couple of years ago, people rethought the sort of basic assumptions that go into number systems. Okay. One thing I should briefly mention is that this is not the only number system out there. So floating point is by far the standard in computing, but there are some cases where you want to do something else. So for example, one simple one is to store things with what people might call infinite precision. So one example of that is, let's say that the only operations I will ever have in my code are add, subtract, multiply, and divide. Yeah? Well, here's the thing. Let's say that I have a number that's a fraction, and I add it to another fraction. Then, fun fact, the sum of two fractions is itself a fraction. So one thing that I might do is define a new number format, which is the ratio of two numbers, a and b, which are both integers, right? This is an example of something I might call an infinite precision number format, right? Because essentially, I don't make any error at all. I just have kind of more complicated arithmetic rules to implement. Does that make sense? So now I store a value by storing two numbers, like the numerator and the denominator. Now, this is a super cool idea. It's actually very easy to implement in like operator overloading in a way that's kind of transparent to the user. But there's some problems with it. So for example, one thing that you may or may not know is that 1/2 is equal to 2/4. And of course, what does that mean in the context of our number system? Well, it means that there are multiple ways to represent the same number as a ratio of two values, right? So when you implement a number format like this, you have to decide, for example, do I multiply things together and then do all the like simplifications and prime factors and all that good stuff? Do I just make peace with redundancy? And now if I have like, I ask a question like, are these two numbers equal? I have to do kind of a more complicated calculation to figure that out. Those are all options, and they're engineering decisions you have to make. Does that make sense? Similarly, it's actually very easy to get blow up in this number system. So here I've taken like what, I guess 6 pretty innocent looking values in fractional arithmetic and added together and gotten a pretty crazy thing on the right-hand side. So these calculations blow up pretty fast. And finally, if I want to do something like compute a square root, I'm kind of hosed. Does that make sense? So that's not the beginning and end of the story. There are all kinds of cool and exotic number systems out there that people have implemented in different applications. So for example, you might say, okay, so if I have square root of 2, then maybe what I'll do is start storing numbers as a over b plus square root of c over d or something like that. Now I can do square root of 2. That's all good, and then I want pi, and I'm in trouble again. Right? You laugh, but actually, for example, in my field, which is computational geometry, people do this very carefully. So there's a piece of software out there called CGAL, Computational Geometry Algorithms Library, and it is templated over number type. And the reason is that in geometry, actually, people have very detailed understanding of precisely what types of numbers you're likely to face. So for example, if the only things you ever do are compute lengths of lines, then like this number system is probably fine, right? And so essentially, one thing that you can do is kind of scope out, this is my algorithm, these are the operations it's likely to use, and then choose a number format where you know that you're never going to leave it. A different thing that you can do, which is kind of lazy, is say, okay, I can represent numbers as a piece of code, right? So I have maybe just integers like 2, 3, 4, 5, 6. And now if I store the square root of 2, rather than doing anything numerical at all, I just store the expression square root 2, right? And this is obviously infinite precision, and moreover, I can just keep adding operations to it to make things, to expand my number system, right? I could add pi and e and whatever else I want into there, yeah? Unfortunately then, there's a couple drawbacks of this kind of system. Now, in some cases, this is really critical. So for example, in geometry, the difference between lines that intersect and lines that are parallel is numerical precision. So like if you're doing calculations in that domain, it might be that you actually want to use a format like this. But now I could ask you a really innocent question, which is, are these two numbers equal to one another, right? And my numbers are defined by some giant like parse tree of code, right? That's actually kind of a complicated thing, right? Like it's not obvious how to take two pieces of code for generating a number and check if they generate the same thing. Yeah, you need all kinds of arithmetic rules. So for example, let's say that I add to my system not only square roots, but cosines, right? And I have a piece of code like the following, just to be really evil. X equals 7, y equals cosine x, z equals sine of x, and now w is equal to cosine, y times y plus z times z, right? So behind the scenes, what is w in my infinite precision arithmetic? Well, it's probably some crazy tree, you know, with like a 7 and like a cosine and a sine and like a square and all this kind of stuff. What is the actual value of w? 1, right? So if I have like a piece of code that says if w equals 1, which by the way, now double equals is kind of safe because I haven't done any rounding. Notice that this actually incurs a very complicated piece of code that needs to have knowledge of trigonometry in order to check if those are the same, right? So these things get very complicated very fast. I mean, never mind equals, like greater than or equals is even harder to think about sometimes. To briefly call out a few additional number systems, then we'll call it for the day. Another one that I think is very common and probably many of you guys might think of is to bracket. So here I'm going to store two values, which is going to be like a value at the center, and then some what's the word I'm looking for? Yeah, some precision, I guess, like some epsilon, which is going to say I have a value and it's somewhere between a minus epsilon and a plus epsilon, right? And now behind the scenes, I have to keep track of rounding really, really carefully, right? So if I add a plus or minus epsilon to b plus or minus delta, right? Then I'm going to get a plus b, rounded up or down, plus or minus some function of epsilon and delta. And notice when I implement that number type, I've got to be awfully careful about rounding up and down of every single piece of that expression, right? To be conservative about it. This is actually a very popular option because it's really not that much more additional computation than just doing the arithmetic on the A's and the B's. But of course, this error can explode, right? The more expressions I have, the bigger these brackets get, and it's hard to recover. Moreover, suddenly predicates that used to be easy to code they have 3 answers instead of 2, right? Like, does A equal to B? Well, one answer is yes. Another answer is no. And a third one is, right? And unfortunately for us, these are really annoying to deal with in code, right? So for example, I think equal sign is still one that you shouldn't implement in a number system like this. But to check if two numbers are greater than or equal to one another, well, now it's perfectly reasonable to check if the two intervals intersect. But if they overlap, the answer is just like inconclusive, right? And so for some applications, that's just insufficient. Of course, don't delude yourself. When I say insufficient, you could easily get rid of this number system and it'll confidently give you an answer that might be wrong because you rounded. Yeah? So it really depends on your particular setting. I put in the slides a pointer to a really cool research paper from a couple of years ago at SIGGRAPH that actually makes use of these in a really cool way to do certain machine learning style calculations on deep neural networks. There they actually propose an extension of this bracketing strategy where you can kind of think of like that epsilon as the first term of a Taylor series. They actually bracket things in terms of a polynomial, which is kind of cool. And it turns out can add a lot of precision to this strategy. So if you like this kind of thing, I encourage you to give that paper a quick glance. It's like an interesting kind of combination of old and new. So essentially what we're going to really talk about in our next lecture is to expand on the discussion we've had so far and to just talk about how there's many, many sources of error in a given calculation on a computer. And we've already talked about a few. One is rounding, right? Any calculation we do in floating point is going to induce error. But that's one of many in numerical methods, right? So in addition to that, we could talk about discretization error. So for example, let's say I wanted to approximate the derivative of a function f of t. I might choose an epsilon and say, I can compute a divided difference, like f of t plus epsilon minus f of t divided by epsilon. We know for very small epsilon, this is pretty close to f prime, but not exactly the same. So it would have induced an error for a different reason, which is that the right-hand side only approximates the left. That's going to be kosher in numerical methods. In some sense, like that ship already sailed. We're rounding up and down, so like what's some more error? Yeah? But we've got to decide on what's our level of tolerance here. Incidentally, this is a great example of a really subtle trade-off, because you might say, well, discretization error is smallest if I just choose epsilon to be like the smallest possible number on my computer. But what goes wrong? Well, now I'm dealing with really, really tiny values, and probably rounding gets messed up. Yeah? So the error, you probably don't want a really tiny value of epsilon. We'll come back to that when we talk about numerical derivatives. There's modeling error, like we're modeling the weather and we neglect the flapping of butterfly wings in Malaysia, then of course our weather model is ever so slightly inaccurate, and for all we know that expands over time. And then there's input error. So for example, these days oftentimes a buzzword in industry, if you want to get lots of funding, is to go talk to people about digital twins, the idea that your computer has some virtual copy of your factory floor, and like the two are simulating one another, and like some sensor is bringing a relationship between the two. Then of course, if that sensor itself makes a mistake, then like it doesn't matter how high precision your calculation is, you have some error. So this is all to say that this is a research field with a lot of wiggle room. And our goal is going to be to try and essentially bound it, understand it, and to keep track of it as we do all of our calculations. So essentially, what I'm going to leave you with is to think about for next time, what are all the different sources of error that you might have in a financial simulation? So if I have like a nice differential equation model that predicts the stock market in 10 days, we all know that those are wildly imprecise. But kind of go back into that framework that I just gave you and try to find sources of error in each of those categories that might affect your simulation. Okay? And so then once we do that, we'll talk about conditioning and forward and backward error and all the different ways that we measure it in our next lecture. So with that, everybody have a lovely weekend. The first assignment is already on the course website, and you should give it a start. Okay? It's designed to be 2 full weeks worth of effort, and you can already do some of it from today's lecture. Okay? So with that, I'll see you next time.